Let's get started. Good evening, ladies and gentlemen. Welcome to the Calgary Python Meetup. I'm Carson, and it's nice to see you all here. So here at the bottom is our YYC Design Slack channel. So if you have any questions, you can just hop there, or there is also an opportunity channel that people are posting job opportunities frequently. So yeah, feel free to check it out. Okay, next one is our long-term sponsorship collaboration team, Teamit. So Rich, do you want to say anything?
Oh, sure, yeah. Teamit is the company I work for. What we've been doing for the past few years is recruiting remote teams, which is obviously much more relevant now. So a lot of, whether it's Python or other, a lot of open source tech stack jobs. So if anyone's interested, you can always just look me up on LinkedIn or send me an email, rich@teamit.com.
Awesome. So yeah, if your company would like to collaborate or sponsor, please let us know. And yeah, we can go from there. Today's talk. So Tyler will give us a talk on the small changes, big impacts, the practical Python performance stuff. I really look forward to that. And the next is upcoming events. So as you know, PyCon US is coming. It was canceled last year, and this year it's reformed it and taking online. So May 12th to 18th. And there is this DjangoCon Europe in June 2nd and 6th. So it's also online. And if you're curious, just feel free to check this link down below here. There are lots of different events there. So yeah. Some news. Python 3.7.10 is available, and 3.6.13 security updates is available. Django also had a couple of security releases released. So the latest one is 3.1.7 and 3.0 and 2.2. So if you haven't upgrading your Django, please do so. These securities are pretty important. Some readings for this month. The first one is classes and subclasses in Python. So this article, it gave some pretty good examples for classes and class inheritance and that sort of knowledge and code examples. So it's pretty good. The second one is why bother using property decorators in Python. So this article is also good in the way that it gives examples of use cases for decorators. Basically, there are like 4 scenarios described in the article. Data validation, operation, some lazy loading, and debugging and monitoring. The third one is more than functions in Python 3. So this article shows some examples for the function and function annotations. The last one is creating file canaries with Python. This is pretty interesting. It first educates us the story behind the canaries was used in the mining coal, and then extend to how the file alerting system was used in Python with examples. So it was pretty fun. If you participated in the bootcamp we organized last November, I feel like these articles are pretty good refreshment of that knowledge. So yeah, check it out. Yeah, as usual, we have our stats website. So if you're interested, keep an eye on there. And our next Python meetup is March 24th. So mark your calendar. Hopefully I will see you all again there. And yeah, we're always looking for presenters, collaborators, especially at this very time. If you have any ideas or like projects, demos you want to share, or if you know anyone who would like to share, speak to us. And we're always looking forward to it. That's about it. Let me hand it over to Tyler.
All right. One moment here. Let me share. All right. Hang on, I bungled it.
Yep, take your time.
All right, there we go. Let me know when you can see that.
Yep, I can see it.
That's perfect. Yep.
All right, cool. One moment. All right, cool. Hi, everyone. My name is Tyler Blair. I'm here to talk about my topic tonight, small changes, big impacts. So the kind of idea that I made for this presentation was how to make Python applications, or really any applications, but Python one specifically for this presentation, faster and more performant by focusing on smaller things within your code base. So that's kind of what I started with when I was building this deck was what are all the small things that I change in Python that makes it faster? And then as I was making this deck and going through it, I kind of realized that it more turned into a presentation about here's the things in Python that when you do them, they kind of make your entire application slow if it's some of those things that are at the core of your code that run in the hot paths. So at the beginning here, I'm going to talk a little bit about what exactly performance is in relation to Python and like the entire system of your application. And then I'll get to create examples after that, showing what different little things in Python you can change to kind of make things quite a bit faster immediately, and ideas for what doesn't make your code faster. So first, just about myself, I'm in Halifax, Nova Scotia, so I'm not joining you guys from Calgary, but I'm super excited to be talking to you all. I currently work in the public sector, and I had some private sector experience before that, but a lot of what I deal with is working in cybersecurity and working with network traffic and analyzing network traffic. Before that, I was in university, and I'm pretty young, I'm mid-20s, but I've been writing Python and Java for around 10 years, give or take. I had a few years. And I guess a lot of things that I've worked on up to here has been how do I make code fast on the system I have at the time. Like for me, being a broke student or being a completely broke student in high school or university, I was always, I want to do this big extravagant thing, but make it fast with crappy hardware. So that's kind of where I'm approaching. For my background itself, I'm not a data scientist. I'm not an engineer, not really a math genius either. I consider myself mostly a developer, and a lot of my focus has been kind of working within the confines of Python itself rather than really complicated, complex system where to make us libraries and things, which I'll get into in a couple slides just to kind of give you an idea of the approaches that I'm going to be talking about are kind of universal to any paradigm. Just a small little wording before we get into the actual how and who and what and why. There's a really good quote for premature optimization from David Knuth. A lot of you will have seen this. Just to kind of go through it, we should forget about small efficiency. Say about 97% of the time, premature optimization is the root of all evil. But we shouldn't pass up the opportunities in that critical 3%. So basically, if you're happy with how your application is performing right now and it is fast enough, you don't have to really follow along with the presentation. Like everything is fine. So making things fast for the sake of it being fast is fine, but a lot of the really nice discoveries and how you optimize code comes when you really have a problem and you need to find that critical 3%. And finding that critical 3%, I'll go into that just a little bit, but a lot of this comes over time with experience, where you kind of just by I guess past experiences know where your code might be slow in the hot path for that critical 3% before you actually hit performance problems. And there you can start looking at it. But to know where that 3% is, a lot of the time you use profilers. I'm not going to talk a lot about profilers in this presentation, but a lot of finding what code is small and where to start working at involves using a profiler. There's a lot of different ones in Python. I'm just going to talk a tiny bit about the ones here. cProfile is the profiler built into Python. It is a deterministic profiler. So it basically will give you exactly how fast your code is running, because it instruments every single function call at the interpreter level. This adds quite a significant performance hit, so I haven't really used this a lot myself. I've mostly used the following two profilers, PySpy and Python Flame Graph. These are sampling profilers, so they'll sample your application, say like 1,000 times a second, and it'll check where you're running at that time. And then based on that, you can see what functions or routines you are running in most of the time, and kind of get an idea for where your code is spending most of its time. There's also print. This is kind of what I use most of the time. Honestly, I'm not too regimented. A couple time calculations and a print statement, and that's how I do the vast majority of my profiling, even though it's quite dirty. And lastly, Elliot is, I discovered this when I was making this deck. It's called a causal profiler, kind of. Basically what it is it's kind of hybrid between a profiler and a logger. So you can introduce this to your code where you normally do logging, and it will go through all of your function calls, time them, and kind of tell you where they fail. And then out of that, it gives you a pretty nice parsable format that you can stick into Elk or whatever other log parsing engine you have. And I thought I just wanted to mention this because it looks really cool, and it's something that I'm gonna be looking at to use in the next few months possibly, because it solves a lot of issues with not just finding slow code, but also discovering why something failed. All right, so with that out of the way, those are just kind of the little warnings. You don't have to optimize your code if you're not having issues, and to find what code you want to kind of target and fix, you want to use profilers. To go back to the actual presentation itself, small changes, big impacts. What I mean by that is these are small incremental changes. Essentially, your platform, your tech, your language, all that remains the same. You're not making huge architectural changes. And a lot of these end up being repeatable techniques. So I'll get into those as well later. So these are sort of like design patterns in that they're also not golden bullets or silver bullets. They don't necessarily make your application faster. It could make it slower. Nothing could change. But within this presentation, I'm just going to focus on some of them that give you a pretty high return on investment. And a lot of these you'll find if you go on Google and search like how to make Python faster or Python performance, that kind of thing. And when you do that kind of thing, you get a lot of red herrings and a lot of things that don't really make sense to change in Python. So here I've kind of condensed it into some of the big hitters that I myself have focused on over the years whenever I've been trying to make a Python application run fast in the confines of the system it's running on. And for the big impact side of it, these are essentially big performance improvements, or like the resource problem that you were having previously to making these is no longer a problem. Like your boss is happy now, you're happy now, your application is no longer crashing or throttling or what have you. It's really just small things that result in a much larger performance impact than you put effort into. And all right, next, I just want to talk a little bit. This is going to be a little bit confusing jumping topic to topic, but it'll make a lot more sense in a few slides. When you talk about making these sort of performance improvements and performance metrics, I'm going to define what the performance metrics could be or how you could optimize these, but what actually is a performance improvement? Like we could talk about making your application use less CPU, or it just does more. Like, what does that mean? And if you look on Wikipedia, it has a nice definition. I'm just going to read the second half here. Is optimization is the process of modifying a software system to make some aspect of it work more efficiently or use fewer resources. And I really like this definition for two reasons. The first one is there's really two different sides of optimization, where more efficiently that could mean a few different things, but using fewer resources doesn't necessarily mean the same thing as being more efficient, which I'll talk about in the very next slide. But knowing and I guess understanding the difference between these is also pretty important for deciding what kind of technique that you're going to use to make a performance optimization. So here I'm just going to give a couple examples of different resource types that you could look to optimize. Like when you see an issue, it'll have a different thing that you can do to fix it or make it more efficient. So the first one, a pretty good example, is htop, just running on a Linux system. The first thing you can see that's probably pretty obvious is there's 8 cores. They're all pegged at 100% CPU. I mean, that could be good or bad, who knows? The memory consumption is around like 60, 70%. I mean, is that fine? It could be fine. It's all within the context of your application and the system itself. Like for the CPU itself, the fact that it's pegged at 100%, is that a good thing? Like, is your application that's running on there, is it keeping up with the work that it's assigned to do? For example, if it's a streaming system that's pulling in streaming data, is it keeping up, or is there a backlog that's building? If that was the case, then using fewer resources would mean being able to consume the entire backlog while using less CPU. And being more efficient, you would be thinking about using less CPU per unit of work. And if you can use less CPU or computation per unit of work, that directly translates into more units of work that you can fit into your system. And for the memory, I mean, it could be good or bad. Maybe you consider that really high, or maybe you're considering moving to a system that has less memory or a more confined system. It's really within the context of the environment. On the flip side, your system could look something like this. It's the same thing, just with a lot less CPU. Most of the cores are, excuse me, are fairly unloaded. Is that a good thing for an application? It could very well be. If the thing you're running on here is sitting idle, then it doesn't really matter, right? Like you're happy with this result. Or if your application is stuck processing whatever it's processing, like it's not able to keep up with the queue of work coming in, then maybe that's not a good thing. Maybe it could use the system more efficiently. In this case, if it is possible to use the system more efficiently, that could mean using more CPU and going back to something like this, where you're using a lot more CPU than you could be otherwise. To go to a slightly different example of a resource, websites have resources as well. I don't work a lot on front ends myself, but there's a lot of different metrics. One here, for example, is first meaningful paint, which is the time it takes for the primary content of the page to be visible. And in this example, it's 3.6 seconds. Again, is that a good number? It's if it's not, and I mean it's yellow, so to me that sounds like it's not. And if I had to wait 3-4 seconds for a page to load, that does feel pretty slow. Then making this more efficient and using, or I guess painting in less time, say like a second or 2 seconds, translates directly into a better user experience. The page loads faster. And on the very extreme end, with embedded hardware, just an example of a Raspberry Pi with a battery pack attached to it with a battery controller. This has resources too. Like it's embedded, so it's very constrained. There's not a lot of processing power, but more obviously there's a battery pack, which if you're running on battery, it has to die eventually. And if you're deploying this somewhere where you're depending on that battery, what kind of battery life are you expecting? Can you make it better? For example, are you using deep sleep states? Are you having the battery controller shut down the Raspberry Pi when it's not needed? That sort of thing. So this is another kind of resource that you can make more efficient and use less of. So using less battery, directly translates into you can leave that thing running wherever it's running much longer without charging it. And one thing I completely forgot, if you have questions, please remember the slide number in the bottom right, and we can zoom back to the slide you had questions on.
Hey, actually, I have a quick question. For the previous
Yes.
slide, how did you get that?
This one?
Yeah.
So I included a citation down here to where I copied it from. If you visit that page, I'm sure they'll tell you what tool I was running on. I do not know what tool I was running on.
Cool.
Because,
Thanks. Yeah, that's fair
but
enough.
yeah, I don't think it's page speed. I think it might be their own thing, but yeah, I recommend taking a look there, and they'll have a tell it. But yeah, if there's also questions along the way, feel free to interrupt and hit me up.
Oh, Tyler,
All right.
Peter has a question here. It just says lighthouse. I'm guessing he's asking about the last slide, if that was the source.
This thing?
Yeah.
Yeah, I mean, if you go to web dev first meaningful paint, I think it'll show up there. I'm not sure. Yeah, the tool could be called
your
lighthouse.
question, Peter? I'll watch the I'll watch for the Q&A coming in, Tyler. I'll jump in if there's questions popping up in the chat box.
Cool. Sounds good. All right, cool. Next, I haven't talked about the practical aspect of the title slide yet, so just to quickly introduce that and what it means with practical performance, or actually what I think it means with practical performance. First, the dictionary definition of practical: relating to experience, real situations, or actions rather than ideas or imagination. And I kind of like this because how I've always looked at performance is within my own experiences and things that I've done in the past that I know kind of work. And so it's kind of been one thing to the next, one thing to the next, where I can look at a problem and see or have ideas of what might fix it. And if I don't, then of course that's when I go to Google to find new things. But a lot of things that I look at, I'm kind of working on what I've done in the past that worked well. So that's what I'm hoping to bring to you guys today. And when you combine that with practical performance, I would kind of define this as something like this. Impactful changes you can realistically make today when faced with a resource problem. So this is essentially practical tips that you can start looking at to improve performance. It doesn't really necessarily apply to all code or systems equally, because there's going to be changes or issues that you face that require a more complicated solution or specialized solution. There's lots of these. I'm going to talk about that very shortly. But basically, if you can be pragmatic and have a nice, simple, elegant solution to fixing your woes and issues first, then that's a lot better than jumping into complex solutions. So there are non-practical solutions. I'm going to talk about just a few and look them up later as well. So I've just listed a very, very short list, somewhat cherry-picked. So I'm going to go through them just a little bit. So first of all, major architectural changes. So if you're looking at making significant changes to your code base or system, for example, rewriting it in a new language, rewriting it in a different framework within that language or different language, going from, say, a monolith to microservices or back, that sort of thing. Those sort of changes I don't really consider practical, because like it depends on how you make them. But if you make them in the name of performance and being faster, there's a lot of risks to that, because you're not guaranteed it'll actually fix anything. If anything, you'll create a lot more problems, which I'll talk about a little bit soon. But just to say that they don't always pan out, and you have to be really careful with design choices there. Organizational challenges. So these sorts of things are bureaucratic in nature. Pretty much every organization is going to have something to complain about here. For example, maybe you're extremely limited in what software you can install. You have to get legal to sign off on every open source project that you look at, because they have to verify the license and that sort of thing. Or getting hardware or resources is difficult or impossible. or you can't use XYZ like AWS, or there's lots of different things here. But basically, if it's blocked by paperwork, then this sort of falls under this, where you're going to have to wait a while to be able to do this. And again, there's risk to it because maybe it's not going to fix what you want. Number 3, specialized techniques. So there's a bunch of different ones here. I just have a few examples, such as C extensions, C types, NumPy, lots and lots of other ones. These things are fantastic. But going back to, I'm not a math nerd. I consider myself a developer, so I kind of kludge everything to work for me. So I'm more saying that specifically towards NumPy, since I've used NumPy in the past, and when you need NumPy, you need NumPy, and there's just some numerical problems that are just extremely slow in Python, but you can solve in one line in NumPy, and that's the sort of thing when you get there, you know you're there, so that's when you can start looking at that. C types, C extensions, same sort of thing where they are not necessarily difficult to use, but they require an extra layer on top of what you're already doing to be able to use. Number 4, PyPy or other runtimes. So normally PyPy is a drop-in solution, most more or less. I have some slides on this later because that's fun, but there's no guarantee it'll work for you, work faster, or even be compatible with your libraries that you're using in a lot of cases. Number 5, FOMO, fear of missing out. So I included this as like a sort of umbrella term for all of the nice new shinies and new technologies that we have in the 21st century, and say like the last 10, 15 years. There's countless ones. I included a short list here of what I call the modern age, and just some examples like NoSQL, such as like the document databases like Docker, or sorry, document databases like MongoDB, Docker, Kubernetes, serverless, cloud, microservices, monoliths, that thing, that sort of thing. And there's nothing inherently wrong with new and shiny technology. I mean, I'm pretty young, so I like using new shiny things, and I've kind of gotten through that phase a few years ago myself, where using these sorts of things, if you're brand new to them and introducing them brand new, you can really burn yourself in doing so, because there's a lot of overhead in learning this and getting buy-in from your team and organization and so on, because once you bring something like this into the mix where you make your stack and your system more complex, then it's not just you that's affected, it's everyone else that has to learn this as well, learn the debugging strategies, all of that. So I'm talking about simple changes. I prefer to keep things nice and simple. So for this presentation, I'm going to mostly be talking about those. For example, like one quote of a blog post that I like is, let's use Kubernetes. Now you have 8 problems, which is true in a lot of ways. Like I've been learning Kubernetes at home, and like I like it enough. It's just there's a lot of complexity that you add with things like this. However, there is a secret 7th option here that I do like myself, because I am pretty lame in saying that we shouldn't use these, which is essentially Dan McKinley. He has a really nice blog post called Choose Boring Technology, and I highly recommend reading it if you haven't read it. It's a fantastic read, and he has a presentation that he's done about it as well. But his main argument is that technology choices, they don't happen in isolation. They have a scope that touches your entire team, your entire organization, and the system that emerges as the sum of your choices. So if you think of your application and the system it lives in, like if you have it deployed on a single virtual machine or a Kubernetes cluster or a PaaS system like Heroku, all of these, when you add them together, it adds up to essentially how complex or complicated your system is. And as a developer, or even a sysadmin, or anyone on your team or teams that support these, they all have to understand how they all work together at a, I guess, down to the level of each service, essentially. So keeping a simple stack, a nice, easy to understand technology, or even like if you're already using Kubernetes and everyone already understands it, that's fine, because everyone is aware of the downsides and how to kind of navigate issues within it. So the gut of the argument is for choosing well-known technology, because when you get to the nitty-gritty, that it's not the technology that you choose that scales to being super fast or web scale or everything else you can say about it. It's the careful architecture and design choices that you made along the way for your given problem that brings the scale. And I'll talk about that a little bit as well later on when we're going through examples. All right, next, before I get into all the nitty-gritty code and showing you fun stuff, I just want to do a little thought exercise of where your application runs when you're thinking where your Python web app or data processor or what have you is running in the cloud or on premises somewhere. You might think it's on, say, like one of these servers. There's a bunch of racks, there's networking, there's blades, there's storage. You have the whole kit and caboodle here. So it's basically, it feels like you can scale to the cloud, scale infinitely sort of thing. And that's fine. It's true in a lot of cases where you can kind of scale this way. And when you're kind of writing your code with this in mind, your mindset is, oh, it'll be on some beefy server, or we can scale it to 100 instances and we don't have to worry about performance. And when you think that this is what your deployment model looks like, it's really easy to think about that, or think about it that way. And how I think about applications when I'm writing them, when I think about where they're going to run and what server rack they're going to run in, what I picture is this, really, like a little crappy rack mount Raspberry Pi with the world's worst cable connection attached to it, with some old enterprise switches, the UPS, and so on. That's the kind of idea I have when I'm writing an application, is if it can run on Raspberry Pi with the kind of load that I want, at the base level anyway, then it can, when I put it on an actual big server in a server rack, it's going to be astronomically fast. Like I don't have to worry about it if that's my mindset for how performant this thing is going to be. Of course, it's in the real world, it doesn't work that way, where you really can't run your huge website or application on a Raspberry Pi. But it's that sort of idea where plan for the smallest possible, or I guess the crappiest possible deployment you can imagine. And then when you're bigger than that, then it's really easy to continue scaling above where you expect it to go. All right, so that was the first half of my spiel on why performance is cool and what you should be warned of, or I guess be worried of, and the kind of ideas that I'm going to present in the second half here, where we're going to go over just a bunch of little classifications, or I guess not classifications, but classes of changes you can make in Python that may or may not have the effect that you intended. But I kind of wanted to present this as a sort of a show and tell, not so much as a you should do this, this, and this. I kind of went into this putting together a bunch of examples, and I was quite surprised with the results at the end, but we'll get to there. So the kind of things I'm going to go through is some really simple ideas. I'll go through the code and what the actual data looks like in a second, but really these are some of the small changes I'm going to talk about. There's tons and tons and tons of different ones. I've kind of cherry picked these as things that are that I've seen make a really nice impact when you really need it, or something that can really bite you in the butt when you don't expect it. So the first one, be lazy. Unexecuted code is perfect. If you don't execute code, then in the Python interpreter, it's not slow at all, because it's not executed. So I'm going to talk a little bit about that. Generators, Python generators are fantastic. I'm going to talk about the memory savings there, string formatting, multiprocessing, which will be just very short. I didn't want to add this, but at the same time, it's still useful to talk about a little bit. Drop-in replacements. So this is going back to the idea of PyPy and things you can drop in as a suitable replacement for something else. Air quotes caching. Caching is really, really hard, but we'll talk about it a little bit. And lastly, hardware. So kind of going back to your big rack mount server versus world's crappiest Raspberry Pi that you can find. Okay, so for the actual data I'm going to be showing you guys, it's sample data. It's synthetic from a mock network appliance. So my background is in network data processing and metadata processing. So a lot of my work is based off of this, or I guess my experience. So I'm going to talk about this as sort of a pretend we have this sort of data, and this is the kind of things that I've worked with in the past, that making them run really fast with a pretty small server was a pretty good pastime of mine. So it's representative of a larger set of data. Each of the test runs I'm going to talk about, I've averaged them over 5 repeated executions to kind of get out the variations. And the data is going to look like this. It's JSON records. They all have IPs, ports, and a time, which is nanoseconds since epoch, and a protocol. There would be a lot more headers here, but I just include protocol as an example. For example, if it's coming from, say, a NetFlow style agent. So there's HTTP, there's a few others that I had it in here. And we're going to pretend the data slice is over an hour, and there's 2.4 million such records for these network events. All right, so first one, be lazy. Executed code that's unused is bloat. If you can avoid executing code in Python, that's fantastic, because otherwise the interpreter is going to interpret and it's going to run it. It's not going to be nice for you and optimize it away. So there's lots of different approaches here. One of them is lazily computing either properties or functions or really anything you have. And this is one thing that can help a lot depending on how your access patterns look like. So for example, if you have a property that you want to cache, functools, and I think Python 3.8 onwards has a cached property. And what it does is when you call this property the first time, it'll just cache the result and return that to you every single time after that. Behaves just like a normal property decorator. And there's other decorators too, which I'll show later on. And this compute expensive property function would only be called once, of course, for every time you call this property. And secondly, when you're being lazy, and this is a lot of times related to more data processing pipelines, but you want to try to prefer base types over say object wrappers when you're working with data that's in a very hot path. So for example, with the sample data I'll be using with you guys, there's millions and millions of these records. So the very best kind of wrapper that you could use for this is just a nice plain old dictionary. The keys are well known. We're going to pretend there's no error handling or anything like that. So this is the fastest possible thing you can get. So it's JSON. So when you load it, you get a dictionary back. Compared to, say, a little class that you just use to wrap the data directly. And this is not so fun because in the hot paths, you'll be wrapping every single JSON record with an object class. And just to go through a quick example here with how this might work in practice is oh, sorry, I can answer that now. For hot path, what I mean by that is basically a section of code that runs many, many times. So it's the critical 3% of your application where you're spent doing the most work. So if you're iterating over 2 million items, the work that you're doing in each of those iterations, I would consider hot, because if you're doing something wasteful, you're doing something wasteful 2 million times. So if you can avoid doing something wasteful in those in the hot sections of your code, then it's free performance, because that's how many ever times, usually in the millions, that you don't have to do anymore. And okay, so I have a sample function here. So this is just a function that loads a bunch of these records up here from a file. And all it's really doing is it just iterates over every single line. It loads the data and then enriches it. So here it's just getting the date time. For simplicity, we're taking off the nanoseconds portion. And the IPs, we're converting them to an IP address type. So this IP address guy is in Python 3, its standard library. And why this is useful is the IPs here are strings. So if you're working with them at all, like doing GeoIP lookups or any other kind of lookups or mapping to networks, then you want them in a nice friendly type here. And then you can add them to a list and return that list. And then Bob's your uncle, you have all your records. And as a further little thing here, a pretend exercise, I'm looking for all of the network flow events here that match the protocol BACnet, which BACnet is just an industrial control system protocol, which is of interest if there's people accessing it, because it's a very insecure protocol. And all this does is it just lists comprehension. It loads all the records and filters for ones that match the desired protocol, and then returns all of those. And if I were to run this, which I did a few times, if this thing would hide in the bottom left here, the average when I ran it 5 times was 52 seconds, which, I mean, that's quite good. If the data slice is a full hour, then if I can process that in 52 seconds, then that's pretty cool. A lot of what I used to play with was not necessarily streaming data by the hour. It was more, we need to find one little event or I guess a statistic on all of the events within the last 3 months, 6 months, that sort of thing. And those sort of ad hoc queries, you would be scanning all of the data to read everything. So if it takes a full minute for each hour, then that could be, say, like 20, 30 minutes per day, multiplied by a few months, and your application might take a few hours to run, which, I mean, they could be good or bad, but at least when I used to do this exact sort of thing quite often, I would want it quite a bit quicker. So a lot of my game was getting this to run as quickly as possible. And if we were to talk about being lazy, when you're doing the filtering here and loading all the records, you're throwing away a lot of them, which means that any code within essentially here is being duplicated over the span of 2 million records, when we might only be getting back 200,000 or 300,000 records. So one thing you could try or do through experimentation is just delete these out of curiosity. And now this code suddenly runs in 17 seconds, which is a pretty significant drop, 52 seconds to 17 seconds. So this being quite significant or quite representative of the performance of this record loader in general is quite telling. So what you could do is, instead of running this here, you could run them after you've already done the filtering. So on the records that do match the thing that you want, the protocol in this case, just run it on those. And if you do that, you get something that looks like this. So all that really changed here was this guy was deleted and a new function was created here, enrich record. And that's called on every record that matches the protocol. And this is the same code, no difference, just copy and pasted. And it runs in 24 seconds, which is pretty decent. Like it's 17 seconds versus 24 seconds. That's not much more, and it's still a lot less than it was before. So this idea of just not executing code you don't need. It varies from application to application. But when there's this sort of thing, you can really get pretty significant wins. And to go a little bit further, let me just first show you a table of these three. And what was interesting when I found out about this the very first time, a long time ago, was the bulk majority of these 3 lines of code is happening inside this IP address structure, which is weird because when I first experienced this, I figured, an IP address structure object is pretty small. Like all it's doing is converting this string into an integer and just putting nice facilities around it for accessing or comparing it to CIDR networks and so on. But it actually takes up pretty much the entire time that this code is running. So what you could do is, if you can assume that this is getting a little bit into networking knowledge and networking work. So if it's not super clear, that's okay. I just want to mention that this IP address, this IPv4 address, can be represented by a 32-bit integer. So if you do that math directly, instead of using an object, what happens is you can make it run in 19 seconds instead, which compared to the 24 seconds is quite good, but also compared to the 17 seconds, it's barely any overhead to just compute the integer directly from the string instead of wrapping it in this unexpectedly large or unexpectedly expensive IP address structure. And this is the idea that innocent function calls can be unexpectedly expensive. Or when I first found this, I thought the datetime function would be more expensive than an IP address one. So I was really surprised when I found that. And so these kind of things can really creep up and hit you everywhere, where if you have something or a function that you're running thousands and thousands of times, then you can be really surprised with what functions are actually slow and which ones kind of dominate your application. And these you kind of discover when you use profilers and the like. All right, next, I want to talk about generators. So generators, they are functions that act like iterators. And I have an example down here, just a function that returns a list. So it'll return numbers 0 to 10. It'll sleep every second, and then it'll return a list of those 10 numbers, or I guess 11 numbers. And then you can iterate over it as you would any other list or array. And here's the generator example. The only thing that really changes is the return type. It returns an object, a generator object. And instead of keeping a list of all of your results, you can do away with that and change it to a yield. And so this gives you 2 things. The first thing it does is the iteration is the same, but it'll give you your values in, I guess, in order. So when you yield a value, execution will go back to your main function. So it'll immediately print it out, as compared to lists, where it will wait until the entire list is created and then it'll return. So in 10, 11 seconds, you'll suddenly get those 11 numbers dumped to your console. At the end generator, you'll get a number every second for 10, 11 seconds. And generally, most functions that return some sort of list can be a generator. It kind of depends. It really depends on the caller. So this is up to your application. And memory savings, that can be possible. Kind of implying what's coming next here, because when you return a list, you return all the values, and that uses memory. With the generator, there's an object, and you're only returning one value at a time. So to go back to the previous kind of code that I was showing you guys, the load records function returns a list. And so the idea is we can convert this to a generator pretty easily by changing these. So this would turn into a yield, and your return would be deleted. And to kind of give you an idea, I reran the application, ran in 25 seconds, and I also recorded how much memory it was using at the time it finished filtering, which was 2.6 gigabytes of memory, which is quite a bit for 300 megabytes of data on disk, which is not overly surprising because it's both reading the entire file here, but it's keeping all of the objects in the list here. So that's how many ever, like 1.5, 1.6 million extra things it doesn't need because it's filtering. So when you change this to a yield into a generator, this is what happens. You just change the return type, add the yield in, snap that in, and it runs in 26 seconds and uses 660 megabytes of memory, which is quite a significant amount less because it's only returning one thing each time. So when the filter step goes over it, it can completely discard the record. It doesn't have to store it in an array. There's no really memory penalty. You can depend on the garbage collector to reuse that object later on. So it's quite elegant in a way. And yeah, so just to kind of show the end result here, 2.5 gigabytes of memory to 660 megabytes of memory. And the overall runtime is a bit slower. So generators, they can be faster, but in the general case, they're going to be a little bit slower because of the overhead of using a generator. However, they can be a huge boon in some cases, like for example, if you're searching through an iterator, like you're looking for a specific, if you're looking for a specific value or a specific item or what have you, if you're using a generator, once you get to the thing that you want, you can just quit execution. You can break out of that loop immediately. With a list that you're returning, you have to take the memory penalty of storing that entire list and also the computation that the function did to get the thing in that list for all the records after the one that you wanted. So there are some cases where it can be faster, but generally it's going to be slower. Generators are great for memory consumption. So if I see, or if I know I'm going to be writing a function that returns essentially an unbounded list, or a list that can contain a lot of items, a lot being, say, a couple million, then these are the kind of functions that I'm suspicious of, and ones that I kind of look to see, can I make this a generator? Because in those, it's quite a big not performance improvement, but memory improvement, especially if you're constrained on how much memory your system has. Next, I just want to say one little thing about string formatting. If you're not using strings, you should use them. They're fantastic. I love them. They're fast. They're friendly to use, and they're more natural. So they were added in Python 3.6, I want to say. And it finally brings string interpolation to Python. So you just have a normal string with an F before it, and then in any curly braces, you just write Python. So it could be a function call, a variable, or what have you. And you can also do formatting, for example, floats. But there's lots of other things you can do with it that are pretty neat. And in fact, they are actually quite a bit faster in a lot of cases. They used to be a bit slower, but I think as of Python 3.8, I want to say, there was a lot of improvements to making these faster than everything else. And one of Python core developers, Raymond Hedinger, he tweeted last year of kind of how fast each string formatting option is, and F strings are at the top, followed by everything else. Before this, I normally used %. So it's nice to see that it is 2 times faster. If you're having performance issues because of string formatting, then I don't know what to say. Congratulations, I guess, because that's I don't know if that's a good problem to have or a bad problem to have. All right, multiprocessing. I just want to talk about this a tiny bit because it's almost never a good solution. It's almost never a small solution. It's usually a more complicated solution. There's a lot of caveats, a lot of fun issues you'll experience with it, but I wanted to mention it just because it's going to be a good comparison for the next example after this. So if you're not familiar with the multi-threading options in Python, basically Python has threads. Python has a global interpreter lock. So when you create multiple threads, only one thread can actually be executing interpreted Python code at the same time. So if you are running multiple threads trying to run a pure computation task, then the will complete in a little bit slower than what a single thread would complete in, which is not so great. So the Python standard library has what's called multiprocessing, which allows you to create multiple Python processes from one process. And it adds all the nice things around it for managing work through those. So like the interprocess communication. So it serializes, deserializes, handles doling out work and maintaining n number of processes. So it is a nice library. It's fun to use, but there's a lot of caveats. So I just want to show what this would look like if you use multiprocessing. I'm not going to go into it too deep. So if there's more questions about it later, I'm happy to take them. So I'm just going to dump you guys with code. So this is the filter backnet records thing I had before. That was a single line. That was just a list comprehension. And now there's a few different things there. No really real error handling, but it does the job. So it creates a pool, and then it's doing the same thing where it's reading a file and going over every file. And it creates a batch, so like a batch of 100,000 lines, and will then process them essentially in the pool. So it takes the 100,000 lines of events and breaks them up into the number of processes that you have. So it'll have, I think here I have 8 cores. It'll be like 12,000 times 8. And then you have this pool.map function where you give it a function and the arguments you want to pass to each of the little processes. So this little chunk is going to have 8 arguments in the list. So it's going to pass that to, or I guess pass each one to a different process. And there's 8 of them. And then it brings back the results. So the actual function that runs in the other process is this guy. So this runs in a completely separate process. It returns a list now because generators, they can't be serialized between processes. So it has to be a list. And all it does is just loads the line, filters, and then does the same enrichment. And when you run this, something not so surprising to me, but could be surprising. I ran it with 8 processes, and it was 2 times faster, or I guess, yeah, 2 times faster. Somehow it was exactly a factor of 2. I'm not sure how that happened. Memory usage was about the same. And I mean, it's fine. Like I'm not too disappointed with the only getting a 2 times speed up. But the big thing here is there's only one process reading lines from a file. And there's a good question there about if the overhead is related to file read time. And in this case, a lot of it, I believe, is, because that is not the cheapest thing in the world. And with multiprocessing, the other thing is you have the interprocess communication. So all of the arguments, all of the return types, they all have to be serialized between the Python processes. And when you're sending a lot of data back and forth, that's not free. So multiprocessing, kind of the takeaway, is it works best when you can dole out autonomous pieces of work. So for example, if I had 8 files that I wanted to process, I could send the file path of each of them to a different Python process. And that would be fantastic because each process could independently read their own file, process their own records, and then return whatever the output of the work is back to the master process, whether it's like a true false, I did the thing you wanted me to do, or a list of results if you're doing some sort of filter or map reduce type operation. So it's very situational with multiprocessing. A lot of the times you can plug it into one specific function or class and have it kind of act within that class and independently within, independently within that class without really impacting anything outside of it. So it can be a nice way to dole out work in a worker queue, but there's a lot of caveats around it and a lot of issues you can hit. So tread lightly. Next, I want to talk about drop-in replacements. So what these are alternative libraries or runtimes that aim to be faster and mostly compliant with the gold standard. Sorry, I was just looking at time. The rest of the presentation is going to be not too long, so hopefully I'm not going too long for you guys. But yeah, so back to drop-in replacements. These are alternative libraries or runtimes that aim to be faster. Some examples are like the JSON library, there's Ultra JSON, there's OR JSON, there's a few others that are mostly compliant with the standard library. There's requests, faster than requests. I mean, it's kind of in the name, it's probably faster. I checked it and it's actually really fast. CPython, there's lots of other runtimes, PyPy, Jython, IronPython, and so on. Lots of these have caveats, but I'm gonna be just using examples for two of these, OR JSON and PyPy. Kind of not so cherry picked. I just wanted to get two examples that I could look and compare. And so I'm going to be using these in relation to the kind of code that I was showing you before with generators and multiprocessing to kind of highlight what sort of effect these have when compared to a single threaded and multi-process application. For OR JSON, it's really easy to use. Like it's that simple. For my use case, it was completely compatible with the objects I was returning from the JSON.loads. So using it is easy. You just import OR JSON, change your JSON to OR JSON.loads, and Bob's your uncle. It just worked. And the nice thing that happened was it was almost 2 times faster in the single process case. Like it went from 26 seconds to 15 seconds. The memory usage was quite a bit lower, which is also really nice to see. And the multiprocessing one wasn't the most significant improvement, just 3 seconds. So what I think when I see that is a lot of the overhead would be from reading the file in the single process and the overhead of sending a lot of data to each individual process. So there could be improvements there, but this alone, like almost a 2 times improvement just by changing the JSON library is it's actually really impressive. So I can't believe I didn't see this library before. Secondly, PyPy. PyPy is an alternative runtime. Going by their homepage, it can be upwards of 4 times faster. Not all extensions will work. It's not always possible to use everything. There's a lot that are compatible. Lots of popular ones are compatible. OR JSON isn't compatible, so I couldn't use it, unfortunately. But using PyPy is really simple. Just replace Python with PyPy, and Bob's your uncle. And here's a nice little comparison chart on their homepage that kind of shows a comparison between CPython and how much faster or slower PyPy could be. There's no guarantee it's faster because obviously there's a lot of different benchmarks here. So when I ran my 2 examples with this, something weird happened. So speed is redacted for now, but the memory usage improved quite a bit, like over less than half, which is really nice. And same with multiprocessing, just a little bit. And for caveats, I was running on CPython 3.9 and PyPy 3.7. So PyPy doesn't have versions for 3.8 or 3.9 yet. And I'm also running on Windows 10, which might have also had an impact on this. But what was weird and what happened was PyPy was over 2 times slower. And in the multiprocessing case, it was 5 or 6 times slower. And so when I was doing this the first time, I was convinced this was wrong. Like I didn't know why this was so much slower when it should be, I mean, at least on par or just as fast. But I mean, no, I ran everything side by side and it seemed okay. So I kind of came to the conclusion. I mean, I didn't try CPython 3.7 to compare apples to apples, but Python 3.8 and 3.9 have done a lot of really good work on the performance point of view. And the sample code I've showed you guys today, a lot of it is using or calling C functions within CPython. So when you're not doing raw interpreted Python, the overhead, or I guess not the overhead, but the improvements that you get from PyPy aren't as significant. And a lot of the code that I was executing is really within the C environment. And the other thing I thought it could be was maybe it's the just-in-time compiler. Like I ran these examples 5 times, so and it was within the same process. So it theory should have been fine, but I'm not too sure. But when I was looking at going over my slides last night, I noticed something interesting. Was their chart on the front page is using CPython 2.7, which I thought was really interesting because the PyPy version they're using and the CPython version they're using are probably at least 10 years old, and that's fine. But I think when I was searching around for what the discrepancies could be, CPython has really come a really long way in the last 5-10 years with respect to performance. Like 2.7 was not a dumpster fire, but Python 3 really fixed a lot of the warts, and so it's really nice that PyPy is finally there, but I'm not too sure where exactly it fits in at the moment. So that's something that I want to look in more to see why was there such a big discrepancy. But it's that sort of thing where I was convinced that PyPy would be faster, but it turns out it wasn't, at least in this very specific example. So it's more of a warning that it's easy to be convinced that something is going to fix the problem that you have, and then you go through all the work to do that one thing without kind of doing sanity checks along the way if yes, it's going to kind of do what you want. Second last thing, caching, air quotes. Great quote from Phil Carton. There are only 2 hard things in computer science: cache and validation, and naming things. Caching in practice is very tricky and very difficult. It really depends. Sometimes it's really easy to do this. Sometimes it's not. So I put this here because it can help in a lot of cases, but sometimes it doesn't. And where I focus on my caching is with immutable objects. And I'll talk about that here in a sec as well. So in Python itself, caching is super easy. If you have a dictionary, that's a cache. This holds true in really any language that has a hash map of some sort. But Python has decorators too, which makes caching super easy. You just add a decorator such as the cache decorator from functools, and now suddenly your function that does something expensive can now cache based off of the parameters here. So when your get thing gets a thing from the database, it'll memoize it and cache it the first time for every value that it sees. But even though it's that easy in Python and it's so easy to do, it can be deceptive because this is an unbounded cache, which might be an oopsie. If your function that you're caching can return infinite things, then that could be a concern. So I almost never use the cache decorator. I just mentioned it because it's the first thing you see and it's nice and shiny. I prefer to use LRU cache instead, least recently used cache. You give it the number of items you want to cache, and when it's full and there's something new, it'll evict the oldest thing that was accessed within that cache. And it's really nice because you have a predictable memory profile, you have the benefits of performance, and yada, 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 and all of that. But basically, ad hoc caching is pretty easy in Python. You don't really want to cache immutable you don't want to cache mutable or stateful objects because you start to really get into difficult problems. So if you have objects that are expensive to compute but don't really change, or you don't care if they're going to change, then use those. It can really help out in a lot of cases. All right, last little thing I want to peddle is hardware. So where your code runs, it's as important as how fast your code is or how performant it is, because if you're expecting to be running on the crappiest internet connection and compute device that you can find, then your expectations for what you can do are going to be a lot lower than if you kind of think, oh, I'm going to deploy this to the cloud or this supercomputer or wherever you're deploying to. So it's kind of getting in your mind how much resources you need to plan for and how much you kind of think you can scale to later on. And my next example here is a little bit dated, but for example, like if you're running a database in 2021 with a hard drive, then I mean, if you're trying to fix something in your application where you're having slowdowns and your queries are slow, or your database can't handle the load, then there's a more obvious fix than trying to add caching to your application or minimizing queries or what have you. It's adding a solid state drive, a good solid state drive even for a database, that sort of thing. So like fixing issues within your full system doesn't necessarily mean code fixes, but it can also mean fixes to like your front end or your database or other such services. And as well, vertical scaling, horizontal scaling. I myself prefer and peddle scaling vertically for many reasons. I won't go into it too much, but it's much simpler. And if you can add a bigger machine or scale your machine bigger, that immediately gives you more performance out of the box. When you are looking at scaling horizontally across many different nodes, if you're not currently doing that, then that can add a lot of risk and difficulty, because now you have potentially state that crosses more than one machine that you need to account for and have some sort of consensus algorithm and all that fun stuff. Unless your application really can just scale horizontally with no worries about state or anything like that, then that is definitely the way to go. But in a lot of my work, I'm used to, or not used to, but the fact that we would have these big beefy machines available to us to just run our application on meant there was no worries about scaling out. And I found that a lot nicer to deal with, because scaling to many cores is pretty fun, and it's a lot funner than scaling to multiple machines. And just to give an example, so like 10-15 years ago, servers were not super well equipped. These days, you can get just enormous machines. Like, I was surprised with how cheap it is these days for like a 2U bracket mount server with 1 terabyte of RAM and a lot of CPU attached to it. 36K is just the Dallas price, so I'm sure the actual price is a lot lower. And if you want to go to like 2 terabytes of RAM, it's like within 256 core, it's like insane how much value you can get for what it costs, like 128,000. 4, 5, 6 years ago, we would have been paying that price for like 250 gigs of RAM. Like, it's ridiculous how far a single machine can go these days. And that's kind of part of why I say I prefer vertical scaling, because compute is definitely going up, but it's something that is easier to deal with. All right, in closing, just a couple last things to kind of, sorry, I can take a drink here. To kind of summarize everything I've talked to so far, understand your entire system. So your system isn't necessarily just your little Python application that's as slow as heck. It includes everything as part of it. So not just profiling your application, there's also understanding, like, if you're a website, you have the machine where it's hosted at. Is it behind a content delivery network? Is it just this one machine in the middle of nowhere? Is there a reverse proxy? Could it be optimized as well? Like, For example, could you change your kernel tuning parameters to handle more connections if you're having issues with connection exhaustion and that sort of thing. And for your application itself, there's of course lots of changes you can make there, but sometimes you need to consider the entire system that you're trying to make perform better. Secondly, find your critical 3%. This really comes from experience using profilers. Using profilers is the biggest thing because they don't really lie. They can lead you in the wrong direction or tell you this wrong sort of thing. But by and large, they're there to help you. And once you find that critical 3%, the 3% where you spend the most of your application's time spinning cycles, then that's what you kind of want to focus on and fix. And lastly, because I like to spiel it, embrace boredom. Like creating complexity is fantastic, and it's something that you kind of have to approach at some point. But as long as you're using a well-known system that you understand well, you know how to scale, you know how to make it perform better, that is, to me, it's a lot more desirable than moving to a completely unknown, complex system that really requires a lot of, I guess, deep knowledge and learning. But this has been my little spiel on small changes having big impacts. Thank you so much, guys. Happy to take questions. I think there's a couple here that I saw but missed.
Oh, that's perfect. Oh, yeah. If you want to
Yes.
jump to the questions, if there's any other.
Yes. So Alex, in the code example, it's probably a good idea to use LRU cache with the get IP function. I completely agree. That's a really good one. One, I really wanted to go through like a little case study with of how you might apply small changes along the way through a development pipeline. And this is exactly one of them that came up, is doing geolocation on millions and millions of IPs really quickly, backed by like a SQLite database. And caching is one of the core things that comes with that and making that actually work well. So that is one good spot that you'd use it. And the last thing before that, I guess it's not really a question, but with the file IO bottleneck, probably makes sense to use multi-threading or async IO. Yes, I would agree. For me, I kind of, if I'm using, say, multi-threading or multi-processing, I prefer to dole out a single file to a process to read and handle entirely. The example here with reading it in one process and then doling out lines to each process really slows you down, but for the purposes of showing you what kind of impact that can have, it was a fine example. Any thoughts on regular expression match performance? Yes, I completely forgot to include that, but regex in Python is actually really fast. I wouldn't be surprised, actually, yeah, I would not be surprised at all if it's faster than most string parsing things in Python, as long as you have a nice, well-formed regex. Is there a dartboard behind me? Of course, Mitch. I knew it would be that. No, that's a fuse box. Fortunately, it's not a dartboard, unless you want to play darts with electrical cables. Avoid the electrical cable.
I think that's all the questions. Do we have more questions coming? Yeah, seems good. That was a really nice talk. A lot of info for sure. And seems like you didn't cover the coroutine when you were talking about the multiprocessing and multi-threads. But that's okay.
Yeah, I don't want to go
things.
too deeply into that because
yeah, definitely.
Multiprocessing is really tricky, and doing it the nice way could be an hour by itself.
Yeah, definitely. If
So
not
we can
more.
put you in for next month.
Yeah, let's do a deep talk on the multi-threads, multiprocessing, and coroutines. Yeah. All right. Seems like that's it. So let me put this Python license draw link in the chat one last time. And if you would like to participate in the draw, Tyler, there, you want to try your luck?
No, that's good. I
Sure.
was awarded enough by coming here.
Sure thing. Down here. Okay. So yeah, if you feel like participating in the draw, please stay. I will do a live draw after the closing. And yeah, I guess that's about it. Thanks for the wonderful talk. Anything else, Rich?
If anyone feels like doing a presentation next month in March, just drop Carson or I a note, and that would be great. Maybe Mitch wants to go for round 2 there.
Yep, there we go.
Yeah, step up,
March,
Mitch.
April. Choose your favorite month.
Yeah.
Yeah, feel free to contact us for sure. All right. That was a great talk, and have a great evening, everyone. And I will see you all on March 24th. Yeah, have a great evening.